Hello and welcome to another WJEC A-level physics question. This time is a PH5 Unit 5 from June 2014 question, and it's question 6 on the paper. It's an electromagnetic induction question about a rectangular coil rotating in a magnetic field, a uniform magnetic field at a uniform or constant angular velocity. We're given the number of turns of the coil at 42. We're given the cross-sectional area as being 22 centimeters by 15 centimeters. First thing we have to do is calculate the flux linkage of the coil for angles of -10 and 10 degrees. Well, flux linkage is n phi, and phi is AB cos theta, so flux linkage is NAB cos theta. Number of turns is 42. To find a cross-sectional area, we need to multiply the two dimensions of 22 centimeters and 15 centimeters by each other, but they need to be in meters. 22 centimeters is 0.22 meters, or 22 times 10 to the minus 2. Same with the 15 centimeters. The field is 0.184 Tesla, and I'm going to start with the -10 degrees. We put those numbers into a calculator, we end up with 0.251, or 25 will be precise enough, I think, and that would be Weber turns, or just simply Webers if you like. Now, because of the shape of a cosine curve, so if I just very roughly sketch a cosine curve here, we know that a cosine curve looks something like that, very badly drawn admittedly, but it's actually symmetrical around 0 degrees. So the value for cos of +10 will be exactly the same as cos of -10. So we can just complete this by saying that the answer is the same for 10 degrees. Next, we're asked to explain why the mean induced EMF is 0 as the coil moves between those two positions. Well, Faraday's law tells us that the induced EMF is the rate of change of flux linkage. And in this case, there is no change of flux linkage. Or no overall change of flux linkage here. The flux linkage does change as it moves from one position through 0 to the other, but there's no overall change, and hence there's no mean induced EMF. Next, we're asked to calculate the mean induced EMF in the coil when the angle changes from 80 degrees to 100 degrees. If the period of rotation of the coil is 0.1 second. So we can use Faraday's law. E equals delta n phi over delta t, rate of change of flux linkage. So for delta n phi, we can use n, which is again 42, times the same calculation for the area of 0.22 times 0.15, times, and we can simplify this by doing cosine of the final angle, cos of 80, take away cosine of the initial angle, cos of 100 degrees. So that's just NAB, sorry, I've missed out the B in here, so I'll just stick that at the end. It's NAB delta cos theta. Notice that's not the same as cos of delta theta. To find the time, we need to realize that we're only rotating through an angle of 20 degrees. So we've only got a fraction of the period. We got 23/60ths, or 1/18th of the period. And the period there is 0.1 seconds. If we put that into a calculator, we end up with about 15.9 volts. Or 16 volts, and we're not going to be too worried about whether it's a plus or minus sign there. Then we're using an oscilloscope to display the sinusoidal EMF in a different coil rotating at a frequency of 12.5 Hz and producing an RMS PD, a root mean square PD of 12 volts. The oscilloscope settings are 5 volts per division vertically and 20 milliseconds per division horizontally, and we've got a sketch of trace that might be seen on the oscilloscope. Nowadays, we would only find this type of question in the alternating currents option in Unit 4, but let's run through it for completeness. So first thing I'm going to do is I'm going to calculate the period of the AC by doing 1 over the frequency, 1 over 12.5. It's useful to put that answer into milliseconds because we're told in the question that the time-based scale is 20 milliseconds per division. So what we've got there is an answer of 80 milliseconds, 0.08 seconds, or just simply 80 milliseconds. To find the peak voltage, we're going to use the fact that the RMS voltage is the peak voltage over root 2. So the peak voltage is going to be root 2 times the RMS voltage. Again, covered in the AC option. So we've got root 2 times the 12 volts. Let me just work that one out quickly. That's basically just under 17 volts. So we'll call it 17 volts. Next, we would label, well, we don't have to, but I would personally label the axes of this graph, which is effectively what the display of the oscilloscope is. So in the vertical direction, we need to get up to about 17 volts. So an obvious scale would be 5s, but we're actually told in the question that it's 5 volts per division anyway. So we can see that our graph is, or our curve is going to fill most of the vertical direction there. The time scale is 20 milliseconds per division. So we can have 0, 20, 40, 60, 80, and so on. Trying to write a little bit smaller to fit everything in. Not worried about labeling with sort of voltage in volts and time in milliseconds because it's not actually a graph. It's just what the display is going to look like. I'm going to draw a sinusoidal variation. You could use cosine. It doesn't really matter. We're just showing generally what the shape would be. So with a period of 80 milliseconds, we know that we're going to complete one oscillation after 80 milliseconds and 2 oscillations after 160 milliseconds. Halfway through the oscillation of a sine function, we're back at 0. So I'm going to add some zeros at these extra points. A quarter of the way through the oscillation, we're at the maximum value. So 17 will be roughly there, minus 17 roughly here, and so on. And then, as well as I can draw it on a screen, I'm just going to draw a relatively smooth sine function there. And that's the end of the question. So